Finding high-level semantic information from a point cloud is a challenging task, especially when this cloud is noisy and sparse. Here, we propose an incremental primitive modeling method that uses both geometric and statistical analyses for such point cloud. Our method uses the generating process available in Visual SLAM systems to evaluate the estimated primitives. When this system reaches a keyframe, it updates the map, which adds new points to it. Then, we use efficient ransack to detect the shapes every time we have a new map. However, some of the detected shapes may be wrong and are not reliable due to a noisy input data or the small number of points on the map. Since most of the characteristics appear at highly textured areas, a primitive may be detected as multiple ones. Therefore, it is important to combine them to improve their reliability. We use the similarity of the shape parameters to decide whether to fuse two primitives or not. When they are fused, the parameters of resulting shape will be the average of the original primitives. We use the intersection of the 3D bounding box and the distance between the center of mass to match the detected shapes with those previously found. We computing a matching score, which is proportional to the intersection volume and inversely proportional to the distance between the center of mass. The shape detected on current frame inherits the history data of the one it matched on previous detections. Here we check if the current shape has a different class from this historical information. If it is not the same, we change to that type of primitive. We also evaluate shapes that were not detected on the current keyframe but appeared previously to recover them if necessary. To compute the reliability of each detected primitive, we first perform a geometric evaluation, which is based on the average distance of each input point that was used to estimate the primitive to the resulting shape. Even for noisy data, this distance will be smaller on correct estimations than on wrong ones. We use this distance to compute a weight for each detection over time. However, in some situations, it is not possible to tell the reliability based only on this weight. For that cases, we perform a statistical analysis that evaluates if these uncertain detections over history are random or not, and only the non-random are considered reliable. The experiments indicate that our method was able to improve both precision and stability. It was observed that representing a shape using primitives requires almost 9 times less memory to describe the scene than using the point cloud. Moreover, the evaluation also suggests that it is possible to segment more than 70% of the point cloud.